8 lah. I'm taking it for my friend.
Hi. Can't get the sound to work, which I vaguely remember having had that problem last time too. Oh, bad.
Cheese and crackers. Of course, yeah, no weapon. Actually, you know, I got a ton of
And officially we ended at 11:50, is that right? Or is it 12? Doesn't matter to me. Do we officially end at 11:50? Like, do I need to cut it off then, or? Mm.
So almost done, right?
Do you want the microphone?
I guess so.
Oh, there is another one.
Yeah.
Right there. Yeah.
That's on? Yes. So, how does it go? Just talk? Okay, so hello everybody out there. I hope that there's lots of people joining us today. This is a center-wide webinar. We've been carrying this about once a month, and we have had lots of audience out there. The one today is going to be offered by Heike Hoffman and Eric Hare, Dr. Eric Hare, I should say, because Eric defended his PhD dissertation on Wednesday successfully, of course. So we're very proud of him. Just a couple of announcements, some upcoming events. The next center-wide webinar is going to be held on May 4 at 3 p.m. Central time. And I apologize to our colleagues in Israel and maybe to some of our colleagues in Europe for the time. We realize this is not convenient. We're going to try and do better. The next webinar is going to be presented by Dan Murray and his colleagues at University of Virginia. And finally, I want to remind everybody that on June 7, 8, and 9, we have an all-hands meeting at Iowa State, and we expect many of you to hopefully join us. If you're interested, make sure to contact us, and we will share details with you. So without any further ado, I'm going to pass it on to Eric, who's going to tell us about 3D bullet analysis. Thank you.
Okay, thanks for that introduction. My name's Eric, and I am going to talk about bullet matching, some of the research that we've done at Iowa State over the last couple of years. I know some of you have seen variations of this talk. There will be some new results towards the end, which we will get to for those of you who have. And again, if you do happen to have any questions during the talk, I guess type into the chat, and then I'll be made aware that someone asked the question and I can answer it. And I will take questions at the end as well. Okay, so a little bit of background. What is the goal in this process? So we're trying to determine whether two bullets were fired from the same gun barrel. And essentially the way we can do that is because, sort of like a fingerprint, it's assumed and mostly shown that the striation patterns or the individual characteristics that are imprinted on the bullet after the bullet is fired are unique to particular gun barrels. So essentially a bullet comes out of a gun barrel, it gets a unique kind of pattern, a striation pattern. And so what generally happens in this process is the forensic examiners then are shooting bullets from the guns of the suspects. So for a crime, you recover the guns from the suspects, you compare it to a bullet that you might have recovered from the crime scene. And if that was the gun that was used at the crime scene, you'd expect that those striation patterns would tend to line up. And you can kind of see under a comparison microscope that a forensic examiner uses, it might look something like this as they're trying to line up those striation markings that go across these horizontal markings. And that works because essentially what happens is the rifling of the barrel imprints sort of this pattern on the bullet. So it's not always exactly like this, but at least for the bullets that we're working with in our test data, the Hamby study, there's this kind of rifled pattern where there's a land impression, then a groove impression, then a land impression, kind of going around the surface, the circumference of the bullet. And that's imprinted by the rifling of the barrel itself. Those are made when the bullet is fired, and what happens is the markings tend to be made on that land impression region. So for the bullets that we're working with, there's 6 different land impressions and 6 different groove impressions. And that's sort of like the geometry of how this works. So what is the current practice? So traditionally, again, they're placed under comparison microscopes, manually aligned. Forensics examiners do a great job at this, but there have been thresholds established as standard practice that maybe aren't as statistical as we like to see in practice. So for instance, a common standard threshold that's been established is if you find 6 consecutively matching striations, then you declare that that bullet is a match, because they've never found bullets fired from the same gun with more than 6 consecutively matching stria. So that's kind of been the one that's used historically. And you can imagine that that threshold, like, you know, if we started collecting enough data, we might find some counterexamples to that claim. And that's why I think there have been some reports coming out in the last decade or so that have kind of put this practice under fire. So the National Academy of Sciences report from 2009 says, for example, bite marks in firearm and tool mark identification, much of the evidence introduced in criminal trials has done so without any meaningful scientific validation, determination of error rates, or reliability testing. So that's a pretty strong statement, and something that could kind of should cause some pause for statisticians especially. And a more recent report, which I think most of us are familiar with now, but the PCAST report from last September, they kind of, you know, they pretty much corroborated that National Academy of Sciences report, and kind of went further to say, how can we solve this problem? And the way to solve it is developing and testing an image analysis algorithm for comparing the similarity of tool marks on bullets. And they did cite some of our work on this as an example of where maybe this field could go to make it a little more objective and statistical in the future.
Right, and then you're measuring the error.
Okay, so without further ado, how did we approach this problem to try to establish some more scientific and statistical thresholds? What we did is we essentially used a reference database of 3D bullet scans. So the NIST ballistics toolmark research database was essentially where we started. So what that gave us is 3D bullet scans, and that made all of this possible. So our goal here and our approach was essentially compute distributional differences between what are called known matches, which are bullets known to be fired from the same gun barrel, and the known non-matches, which are the ones that we know were fired from different barrels. What we did is we derived a set of features that kind of separate these two classes of bullets. We use those features to train a statistical model, which I'll talk about later. And we predict on unknown pairs of bullets the probability of being a match using that statistical model. Of course, the key to this approach, if we're going to actually have effectiveness in this method, is that reference database, that NIST database. So let's talk a little bit about that. So essentially, the data that we started with is the James Hamby study. This is 10 consecutively rifled Ruger P85 pistol barrels. And this is a study that's been done where essentially 20 bullets were fired, and they were known to be, they were considered the known bullets. And then 15 more bullets were fired from some of those barrels, and they were the unknown bullets. They didn't say to the examiners what barrel they came from. And then what they did is they sent these 35 bullets to 507 forensic examiners and asked them to try to identify which barrels did this 15 unknown bullets come from. And as it turns out, the forensic examiners did a very good job. So they had no false positive identifications. They had a few that were inconclusive in the original study, so they weren't able to make a clear determination which barrels. But that essentially formed the basis for where can we make an automated algorithm, a statistical algorithm, do as well or better than these forensic examiners did manually. So what data are we working with? Essentially, the data are 3D topographical images of each bullet. They're in a format called X3P, which I know some of us are probably familiar with now. It's essentially an array of surface measurements done at the micrometer level. There's an R package that's been available called X3PR by Dr. Petrayko at John Jay College. And we started with that kind of for working with the images. We ended up sort of writing our own called Bullet R, which is had a bit more streamlined of a reading routine and some more additional statistical functionality. And then the format for the data, again, if we go back to that diagram from before where we have these land impressions, essentially because we have all these different land impressions on the surface of the bullet, they provide to us the data in the form of 6 different scans per bullet, where each scan covers those land impression regions. So that's sort of what we were working with. Okay, so we have an application where we can kind of show the steps of this. I'm going to talk through the algorithm, and if we have time, we'll come back to that. Essentially, the application is a front end to the different pieces of the algorithm. Question?
Do you know how the data was acquired using what type of?
Yeah, so it was a nanofocus 3D imaging microscope. And so essentially they like put it under the microscope and carefully did these scans, and the scans then produced the surface topologies. Yep. Nanofocus, I forget the exact model, but we do have that. Good question. Okay, so what did we do? So essentially what we sort of started with here is we have, and you can kind of see it here, I'll zoom in. These are sort of how the surfaces of the bullet looks like from our 3D data. So these are 2 bullet lands, a little hard to see on the projector. I hope it's easier on Zoom, but you can see sort of these vertical striation markings that are going across on both sets of lands. And what we decided to do is we would kind of transform these 3D images into sort of a 2D framework to make it a little bit easier to work with. I guess it's kind of common practice to do this. What we were looking for is a place across these bullet lands where we could extract a profile and sort of, you know, capture those striation markings. So you can kind of see along the top here. So this coordinate system starts at 0. Along the top, you can see the markings quite a bit more clearly than along the bottom, where it's a little bit harder to see any striations. And that's a pretty common feature of this. What happens is the top of this bullet land is actually the part that's closest to, is the base of the bullet. And they tend to get the striation markings more pronounced than on other parts of the bullet. So what we're looking for is sort of a region across this bullet surface, with which we can extract a profile and have that profile represent the bullet land in a successful way. So what do we do? Knowing that the base of the bullet is where the striations are most pronounced, the first thing we do is we start at the base of the bullet and essentially do a search for a stable profile. These are sort of the technical details how we did that. Essentially what we're doing is we're optimizing the CCF, or the cross correlation function, which we'll talk a lot more about. We're essentially optimizing the correlation between the subsequent extractions of profiles. So what do? We start sort of at the base of the bullet where we know the markings are more pronounced, and we begin searching up the bullet until we've identified 2 subsequent signatures or profiles where the correlation is high enough. And in our case, we set that to be 0.9. Once we've identified that, that sort of tells us we're at a region of the bullet that's stable. We've identified a stable region where subsequent signatures have a high correlation, which means that probably represents a good profile to extract for that bullet. And since we began at the base of the bullet, we're also really hoping that the striation markings would be more pronounced than if we went higher up on the bullet, which is kind of visible from, again, this image where they tend to be more pronounced here. Okay, that's how we extract our profile. And when we do extract a profile, it kind of looks something like this. So we've gotten rid of the 3D imaging and we're in a purely 2D framework now. And sort of what you can see, you have these what are called shoulders on each end. That's sort of the region in between the land impression and the groove impression. So it's, you know, out to the right of this shoulder where we don't have any data, the groove impression is there. And that's because, you know, when they scan these bullets, they knew that the groove impression doesn't have the striations, so we don't need to include that data for the researchers. The relevant data for us is essentially everything in the middle here, which is the land impression of the bullet. The problem is, of course, bullet surfaces are curved, and that curved structure kind of really dominates this picture. And we're interested in those striations, not the overall curvature, which is just a function of the bullet. You can kind of see it here, so you can see a little bit of a peak there, a few striation markings there, a bigger one here, a bigger one here. but to make working with it a little bit easier, we kind of want to zero in on those peaks a little bit better than what we have just from this image. So what's the next thing that we can do? The next thing we can do is we can say, well, let's get rid of these shoulders. They're irrelevant. They're not a striation. We don't want to trick our algorithm into thinking this is some big striation. So let's get rid of the shoulders and just extract this middle portion. We can do that fairly easily. Here's the algorithm for doing it. Essentially what it boils down to is we smooth out that signature enough so that we know that the very first peak is our shoulder. So we smooth this out and we find that very first peak by looking at where the derivative is equal to 0. And that sort of identifies, okay, this first peak in the profile must be where our shoulder is located. Then we kind of continue down and find the first valley, which indicates the exact location where we should extract the land impression region, which is the center of this profile. That's sort of the details for it. Really the only parameter to optimize here is how much do we smooth the signature. If we over smooth it, we might smooth out the shoulders completely and miss it. And if we under smooth it, we might get some noisy data that tricks our algorithm. So this is sort of what it looks like once we've identified the shoulders. So again, because we can identify that first peak, we can then travel down the profile to identify that first valley and sort of do that on both sides. So what we get is something like this, which identifies sort of the location at which we chop off this image. So everything in the center here is the actual land impression that we're interested in matching. So this is a fairly ideal case right here. It's pretty easy for our algorithm to see this. It's not always this easy, depending on, for instance, where we extracted the profile or maybe the quality of the scan itself. Here's kind of an example, if I can go to it, of a more challenging one. So this is barrel 1, bullet 1, land 6 from the HAMB data. And this, you know, the scan itself wasn't the highest quality, but we also extracted it in a fairly poor spot. And in this case, you can see it's not immediately evident where the actual shoulders are in this profile compared to that other one where it's quite a bit more clear. Maybe it's here, and our algorithm gets tricked into thinking it's actually here. I'm not sure I see it on the right side at all. So it's not always perfect. The good news is that in cases like this, what we can do is we can sort of tell our algorithm, you know, rather than chopping off the image here, let's just use the full profile if we're not sure whether the shoulder was actually identified successfully. So there's ways around the more challenging cases, and most of them are more like this, which makes it nice for our purposes. Okay. So that's identifying the shoulders. So once we've sort of identified those shoulders, we extract and we kind of achieve something that looks like this. So we haven't done anything to remove that bullet curvature yet, but we have removed everything at the shoulders and outside of it. So we get kind of this nice parabola, this arc, where we, again, still see the striation markings, but they're perhaps not as pronounced as they should be if that's really the focus of what we're trying to match for these bullets. So what do? What we do is we essentially fit some sort of model which models that structure of the curvature. We ended up going with a non-parametric model called a low-S regression, which is a local weighted scatter plot smoothing fit. Not to get into too many of the details, but essentially what's happening is it's sort of fitting a low degree polynomial to little pieces of the signature and just kind of going up across the entire signature and profile. And it weights the values in the middle a little bit more strongly. And sort of what it's doing is it's building an estimate of the overall structure of the curve as it does so. And it's a pretty flexible method. It can be used for a lot of different cases. It might not be as popular as some other types of regression, partly because there's no functional form, and actually it's very computationally intensive compared to some other types like least squares and other methods. But it works well for us. It's a little hard to see on the slide here, but that blue line that's going across is actually the essentially the predicted values for our low S regression for this profile. And you can see, roughly speaking, it kind of does fit a fairly smooth parabola, as it should. What we're trying to do is model the structure of the bullet and then extract sort of the deviations from that structure. Question?
So why does that graph have a width or thickness?
Can you repeat that?
Yes, why does that graph have the black one have sort of a width to it? If it was if you have a point on your x-axis and you plot a single point on the y, then why?
Sure. I think it's a function of just what so the question for those of you watching remotely was, why does the black lines, why do the dots sort of have a width or a thickness to them? That was just a function of how I plotted them. So there's a size parameter that I just made a little bit higher. And actually, it would probably have been more clear if I hadn't done that on this. But I was hoping it would still show how the striations deviate a little bit from the blue line by keeping it larger. That's a good question. That's just a function of the plotting software. Okay, so what we get out of this essentially is a model for the structure of the bullet, which is good because then what we can do is we can sort of take our data and subtract that model in order to get the residuals. So subtract the fitted values from the model. And that really starts to zero in on those striation markings. So now what we have is we've sort of flattened out that curvature and focused in on the actual striations on the bullet. And they look so much more pronounced than before, but kind of if you look between these two plots, you can see how they correspond. So this tall one right here that we see, if we kind of go back, you can sort of see that over here as well. And you can kind of play that game for most of these striation markings. And what you find is, yeah, sure enough, most of these are in fact visible on the previous plot. It's just quite a bit more clear now that we've removed the curvature. So this step is very easy, and now that we've arrived at it, we sort of have what we call the bullet signature. So this is sort of like a signature for that particular bullet land. And we're hoping that this signature, if we optimize the previous steps correctly, this signature is a good representation of those markings on the original surface of the bullet. That's the goal. Okay, so now we've extracted the residuals. So sort of the next question is, how do we actually go from this into training a statistical model? Sort of the first step is we need to decide, if you look at this, this is kind of noisy, right? So we see a pretty clear peak here, but you see a lot of like little peaks and valleys that are just noisy right in this region, in this region, in this region. And so sort of the question we want to ask ourselves is, which of these peaks and valleys in this plot are functions of noise or perhaps a variation in the microscope scan or our algorithm, and which are actual striation markings. So again, we kind of go back to, in order to answer that, we can smooth out this signature a little bit and see what we arrive at. So here's one example of doing that. So what we do is we perform the same sort of smoothing step that we did in order to identify those shoulders. And we might get something like this. So this is sort of the red vertical lines represent where we think these are real peaks in the signature. The blue vertical lines are where they're real valleys, not just noise. And kind of going between the previous two plots, you know, you can see this one's identified as a peak, and so is this one. You can kind of see that one there and right there. We might smooth over a bit too many of them. We've kind of toyed with this parameter a little bit for how much smoothing do we really want to do. But this particular amount of smoothing generally worked well for our algorithm. You can see it's not always perfect. Out here, there's something weird happening where the signature is sort of just being a little bit wavy. And so we see peak, valley, peak in just this little region right here. So we're going to run into some errors like that occasionally. But overall, this signature, when it's smoothed out, sort of represents where are we actually seeing the true striations in the data. And now we're starting to arrive a little bit at, we can start to match this with another bullet by kind of performing the same procedure. So that's sort of the next step. Okay, so if we do that same procedure for 2 different bullet lands, we kind of get something like this. So we sort of, these are actually 2, this is real data here. So this isn't just an example. If we look, this is actually barrel 1, bullet 1, land 5 from the Hamby data. And we're comparing it to its known match. So we know that these bullet lands should match. This is barrel 1, bullet 2, land 1. So these are the ones that actually were fired from the same gun barrel. So we'd hope that the signatures do in fact match. At this point, we haven't assessed that statistically. All we've really done is perform those previous 5 steps on each of these 2 signatures. And sorry for switching the colors on you, but now green is representing the valleys and orange is representing the peaks. But otherwise, it's kind of the same thing as what we're having in the previous plot here. So that's what we do. Okay, but that's on individual bullet lands. We also sort of need to perform a little bit of an alignment. So it's not always guaranteed that we're gonna extract sort of the profiles in the exact same place. Oh, sorry. So for instance, if the scan was done a little bit differently or a little bit shifted, we might need to kind of align these 2 to make sure they're lined up. These are already pretty lined up, so this isn't the best example of that. They're not always going to be perfectly aligned without a little work. So once we do the alignment, we might get something like this. And what's great about this is now we can actually start to count the number of striations that match. So that's what we're doing in this step. So you're seeing that anytime our algorithm identifies valleys that overlap, we mark it with an O in this particular plot. So we identify this as a matching valley, a matching striation. This one right here, our algorithm identifies as a matching peak. And what you can do then is go across all the striations that are identified in each signature and see whether they match or whether they don't match. And we can use sort of that data to tell us, you know, some things about the quality of these 2 matches. So in this particular case, this is really ideal. So this isn't a typically standard case, but actually I think every single striation our algorithm says matches. So if we smooth it out enough, every striation detected here matches, which means we can kind of compute some features from that, which is cool. So in this case, I want to say there's something like 25 or so matching striations. So remember, if you think back to the thresholds that I talked about at the beginning, so one of the thresholds that's been used is consecutively matching stria. And we can sort of perform that same computation by looking at this and seeing how many of these striation markings are in fact consecutively matching. But we can do quite a bit more than that. We can extract several features. We don't just have to use consecutively matching stria. So I've already talked about the CCF a little bit. So essentially, once we've aligned the 2 signatures, what's the correlation between them? That's a feature we could extract, certainly. We could extract a D, we're calling it D, which is essentially the vertical distance between the height values of the aligned signatures. So if we had a match, you would hope there's not much of a vertical difference between these 2 signatures. They should align well and there's not too much of a difference. So you'd want D to be low for a matching bullet. So one feature we use is just the raw number of matching striations. So don't think about consecutive, just count the number of matching striations. So we could compute that ourselves just by counting how many O's are down in this plot to get the number of matches. And there's a few more. We can count the number of mismatching striations, which again would be negatively correlated with bullets that match. We did in fact use CMS as well to see how it performs, since it's a standard threshold that's used in practice. And we do it a little bit differently because traditionally CMS, I believe, is only counting the actual peaks. We're including valleys, so we're essentially doubling the traditional thresholds in our computation of CMS. We can count the consecutive mismatching striations. And then one other feature we use is called S, which is essentially for each matching striation, what's the average height of it? So presumably, if it's a true striation and not noise, you would hope that that would be a little bit bigger and a little bit more pronounced than some of these littler ones, which may or may not be noise. those are the features we initially used. And what we can do is we can sort of see how those features actually are distributed based on whether the bullets were from the same barrel versus whether they were not. So you can see this light blue. This light blue in each of these plots is the known matches. So the bullets that were fired from the same gun barrel. The dark blue are the ones that were not. And what you can see, what we hope to see, is that these distributions are pretty well separated, because what that tells us is these features are actually distinguishing very effectively between bullet matches and non-bullet matches. So what do we see? Consecutively matching stria is up in the top left here. And you can see there's certainly a difference between the distributions. So in other words, the known bullet matches do tend to have a higher number of consecutively matching stria. But there's also quite a bit of overlap in this region, right? So there's a lot of bullet matches that have a low number of consecutively matching stria according to our algorithm. You can contrast that with, for instance, the number of matches. So not the consecutive, but just the raw number of matches, where it actually is a little bit more well separated. So our algorithm thinks that that feature distinguishes matches and non-matches a little bit better than consecutively matching stria. Also, you can see probably the best one out of these is the CCF, the cross-correlation function, where almost a good majority of the bullets that are matches have a CCF around 0.9, whereas most of the bullets that are non-matches have a CCF around 0.3. So those are pretty distinguishable groups according to the CCF. Okay. So then final step is we use those features to train a random forest. So what we have here sort of is a tree model and then a random forest model. So for the initial Hamby data, the interesting thing, a single tree, so a single decision tree has quite a few errors. We make quite a few errors. But then once we use a random forest with about 300 decision trees, for the original data, we completely distinguish between non-matches and matches. So these lands here are all the bullet land pairs that are matches, and you can see we assign at least a score of 50% to all of them. And these are all the known non-matches. We're perfectly distinguishing between characteristics. Question? So yeah, these are actually density plots, and that's why they're smoothed out. They're not histograms. That's a great question. So why are they kind of smoothed out and how many points are in them? So the answer to how many points are in them is every comparison between bullet lands in the Hamby data. So there's 35 bullets, which means 210 bullet lands, which means 210 times 210 comparisons, which is about 40,000, if I remember correctly, around there. And then the way we're plotting it, we're kind of smoothing out the distributions. We could produce histograms and then they would look a lot less smooth than this. This is sort of an estimate of the density of those distributions. That's a great question. Okay, so one thing we can get out of our random forest also is the importance of different features. So you can see that our random forest actually thinks that the CCF and the number of matches are the two most important features in distinguishing whether a bullet was fired from a particular gun barrel. And you'll notice CMS is actually quite a bit lower. It's the second lowest feature in our forest. So what that tells us is, at least for our algorithm, these features are a little bit more important and do a better job than the CMS does in distinguishing. Question?
Comment.
Yep.
I believe a 300 tree forest would likely overfit your data given the number of bullets you have. 300 summarize small numbers.
So we assess the forest with an out of sample test later. So and what actually happens is that the out of bag error ends up leveling out at about 100 trees and kind of stays that way up till 1,000. So I don't think it, Dr. Hoffman?
We don't have 300. We've got 216 times 216 pieces of evidence. So just say that the bullet lands are not what we're looking at. We're looking at comparisons of bullet.
Right. Okay. Yeah. I thought I made that clear. So we're not we have 210 bullet lands, but what that means is to train our model, we actually have 210 times 210 comparisons. So about 40,000 data points. And that's why the 300 trees actually doesn't cause a problem as far as overfitting. So our model's trained on all cross comparisons of bullet lands, which is about 40,000 in this initial example. Good question though. Okay, so then this is sort of some new stuff. So our forest did a great job for this ideal case of this one data set. What we wanted to explore is whether we could sort of generalize our algorithm to handle the case of degraded bullets. So maybe we don't actually recover a full signature. So we recover actually a fragment of a bullet land. And will our algorithm actually handle that case? So in order to do that, we sort of needed to take a few additional generalization steps. The first one is we actually needed to rethink some of these features. So here's an example of two aligned bullet signatures like we saw before. And what we can do is, again, matches is one feature that's very important. So we can count the number of matching striations. In this particular comparison, that would be 27 matches. One thing we can do, if we're factoring in the case that we might have only recovered a portion of a land, is we can standardize that by essentially the length of the overlap. So if we standardize that, and instead of thinking about matches, we think about matches per millimeter, what we get for this particular example is 14.72 matching striations per millimeter. So why do we do that? The reason is, imagine a case like this. So in our old algorithm, if we had a case like this, we'd compute the number of matches, say that there's 8 matching striations, because that's all we really have in this particular fragment. But that would really kind of arbitrarily punish this comparison. Our forest would say, oh, 8 matching striations is usually not indicative of a match. And it would kind of declare it, okay, that's probably not a match. If we standardize it by the length of the overlapping region, instead we get matches per millimeter in this scenario of 11.42. So we get something that's pretty similar to this previous case, which is good because it means our algorithm then could see that, even though the number of matches is pretty low, it's doing a really good job in the region at which we have data. And that's why we standardize the features. So we can actually do that for every feature at which that's important to do so. We don't need to do it for the CCF because that's still computable. And we don't need to do it for the vertical distance, the average vertical distance. But some of these others like matches and mismatches, we essentially just standardize it so that it's dependent on the length of the signatures involved rather than just a raw value. There was one other problem our algorithm had that we wanted to tackle that's kind of related to degraded bullets. When there was a large vertical deformation in the two aligned signatures, our algorithm would tend to be a little bit tricked. Here's an example. I'll zoom in a little bit. These are two bullet signatures here. And you can see what happens is even though the actual striations don't seem to line up very well, there's sort of this weird vertical like chunk here. And I'm not actually positive what that came from. It could have been dust on the scan. It could have been any number of things, but both signatures actually have this. So they both kind of follow the same general pattern where there's this big vertical deformation, even though the individual striations themselves don't align very well. And that tricks our algorithm because what ends up happening is our algorithm says the correlation between these two is quite high because they have sort of the same general structure. As a matter of fact, in this particular case, the CCF was 0.77, which would usually be indicative of these two bullets being fired from the same barrel. So what do? We essentially fit one more low-S regression to the average of these two signatures, and that looks something like this. So this thick blue line, it's a regression fit to the average of the two signatures. And then what we can do is we can sort of take our original signatures and subtract that fit to arrive at something that looks more like this. So you'll notice we've sort of removed that big vertical deformation. And we call this roughness correlation because I guess the idea is that this focuses more on the roughness of the bullet rather than the waviness of the bullet. And what ends up happening is even though CCF is still tricked, our roughness correlation sees that there's essentially a zero correlation between these two signatures, which is good because we know these are actually not fired from the same gun barrel. So roughness correlation helps us in cases like this. It's not always super helpful. Here's an example. In a more typical case where we have a normal sort of matching set of signatures, the roughness correlation might look something like this, and then we get these two signatures, which you can see doesn't look too different from the original. And so this doesn't actually help us in these cases, but it doesn't hurt us either. Question?
Comment.
Yep.
Differences in profiles is quite common in long comparisons. One bullet might be engraved more heavily than a second bullet, but the profile patterns be similar.
That's a very interesting comment. That's a good comment. In this, I think what ends up happening is in cases like that where it's actually a function of the bullet itself and we wouldn't want to lose that information, the striations themselves should still line up and our algorithm would do an okay job with it. So really it's for the cases like this where they aren't matches and the actual striation markings would show that where it helps us. So I hope that it's not harming us in cases like that where these actually are features of the bullet that we want to include in the comparison. So that's a really good point. Okay. And just to illustrate again, I think I flipped the colors from the previous example of this. Now the known non-matches are light blue and the known matches are dark blue. But you can see the CCF, again, very well distinguished like we saw before. And the roughness correlation is also extremely well distinguished. So it's sort of showing us roughness correlation. We expect that there's a high value of that for bullets fired from the same gun. For bullets that aren't fired from the same gun, it's usually going to be about zero, which is exactly what we see in a case like this. So that's a good validation of the feature. Okay, so what did we do to kind of take steps to address the degraded bullets case? Essentially what we did is a simulation study. And what we did is we sort of simulated 3 different scenarios. Where essentially left fixed, middle fixed, and right fixed, where left fixed essentially means we recovered the left-hand side of the signature. Right fixed means we recovered the right-hand side. So for instance, this is an example of a left fixed degraded situation because we have the left side of that signature in our coordinate system. And we sort of picked different degradation levels. So like 100% would be a fully recovered bullet land, which is the normal case. And then we went all the way down to about 25%, so a little tiny fragment of that signature. And we sort of passed it into our algorithm and tried to see whether with standardizing our features, could the forest still distinguish even at different degradation levels like this? Question?
So you have, if the graph shows there's missing data, does the regression fill that in?
Yes, it would. Yep. So if there's like missing points, it will smooth through that essentially.
What's the definition of a degraded bullet?
So in the real world, that could be a whole wide variety of things. Like for instance, you recover a little fragment of a bullet. In this particular case, we're kind of simplifying it to be more like we recover a full section of one side of the bullet. So this is definitely a simplified case. In a real world scenario, we might recover a piece here, a piece here, a piece here, depending on what happened when the bullet was fired, and if little pieces broke off, for instance.
So does degraded mean that you don't have a complete signature with enough sample points?
Not in our case. So no, in our case, we're not actually caring about the number of sampled points. We're caring about just that we're simulating lengths of signatures that are much smaller than the ones that we use to train the model, essentially. So degraded in our case means much smaller signatures than we did to use to train the model. And for a 9mm bullet, this is a very standard case, about a 2mm land. And then this would be something like a 0.5mm or a little bit more than that in this case. Okay, so that was our simulation. So what did we get when we simulated? It's actually pretty interesting. So first of all, the two panels here are the sensitivity and the specificity of our results. So the sensitivity, for those of you who don't know, is essentially like the true positive rate. So how good are we at detecting the true bullet matches, detecting the bullets that were fired from the same gun barrel. And then the specificity is the true negative rate. So how good we are at detecting the true negatives. And so what happens here is, first of all, we have our baseline, which is our full case. We're very specific because essentially we're good at detecting the true negatives. We don't make very many false positives in our model. We're not as sensitive in our original case for the full model. But you'll notice this pattern. So what happens is up to about 50% of the land being recovered. So if we go down to about a 50% proportion of that land, we're still actually doing relatively good job. So our specificity is hanging near 1. It's definitely beginning to decline. And our sensitivity has declined to about 0.6 from originally 0.7. But then what happens beyond that? Here's where it gets interesting. At about 25%, you'll notice it's really gone into a nosedive. And what's happening is because we've only recovered about 25% of that signature is being overfit to the overall profile. So when we do the alignment, it's sort of finding a good spot in the other profile, even if these bullets don't match. So our sensitivity is rising because we're starting to declare a lot more positives. We're starting to say a lot of bullets that actually weren't matches were matches, and we're kind of correctly identifying some of them. So we definitely prefer the cases out here because making a false positive seems like a pretty bad error. Out here, we're making a lot more false positives and a lot more true positives. And here's the basic reason for that. You can see the feature expression. So these are our different features as a function of the degradation for each of these cases. The CCF is actually kind of on a rise as we decrease the length of these signatures. And that's essentially because it's being a little bit overfit. And that's what's sort of happening here. So essentially, once we get out to like a little bit below 50% of a land being recovered, we're really starting to cause issues with our time, with our algorithms allotment and deciding whether it's a match or a non-match. And then just to kind of wrap it up, here was sort of how we ended this. What we decided to do is to see whether we could match this particular bullet by only extracting this half of the bullet. You'll notice there's pretty bad tank rash on this side. So we had initially actually excluded this bullet, which is barrel 9, bullet 2, land 4, from our algorithm. But now that we saw we could match about up down to about 50%, we decided to try to extract the first 50% of this bullet and feed it into our algorithm to see if we could identify its match. It was a pretty interesting result. What actually happened is for that 50% degraded land, our algorithm was barely able to identify it. So it said 51% match probability. Whereas if we use that whole land where we have that bad tank rash, our algorithm only said about 1.67%. So it was a good validation that by standardizing these features, our algorithm is actually able to see some matches that it otherwise wouldn't have been able to because of situations like this where we have damage or degradation on some side of the bullet. Okay. That was pretty much all I had. I was just going to briefly say some future work. Essentially, the biggest limitation of these algorithms at this point has to do with our reference data. So as we continue to get more data, we should be able to continue to improve it. So right now, we've really mostly done all this assessment on the Hamby data and a little bit on this carry persistence study. And as more data is collected, we should be able to kind of continue to improve on it. There's some work to be done with parameter optimization. So a lot of these algorithms I've talked about, I said we've used this value for the parameter. We've optimized some of them, but really there's more work to be done as far as optimizing the parameters for a wider variety of cases rather than just the barrels from the Hamby study that we're using right now. I guess that's all I had. I wanted to give a special thanks to Alan at NIST, because the database essentially formed the foundation for us to be able to do this. And he's been immensely helpful every step of the way in kind of helping us out with improving this. And with that, I'm open for questions if anyone has it. Question here first, yeah.
So, did you try several different types of regression fits before deciding?
So the question was, did we try several other regression fits before deciding on the low S? The answer is not before deciding on the low S, but I did after deciding on it. So I did try a smoothing spline, so another non-parametric fit. It ended up being about, as far as I could tell, I didn't do a thorough assessment, but about equally as powerful. It worked as well for our algorithm as a low S did. And we also did try one other, which is a parametric fit, which was a circular fit. That one didn't work as well because, as it turns out, the shape of a bullet actually isn't quite like that. And so it needs to be a little bit non-parametric.
Do you think that the results, this whole process would vary depending on what type of regression fit you decided?
The answer is definitely, because essentially our signatures are completely derived from that. But ideally, if you had some effective model for that actual structure, it shouldn't vary too much. So if it's doing a good job of capturing the curvature, I wouldn't expect the results to change too much. It's a great question. Yep.
2 questions.
Okay.
First one, I'm just wondering how long it takes to do these computations. For example, if we have a new bullet and some large database, would you be able to do all pairwise comparisons fairly quickly?
Great question. So we actually just started running these computations on a new server. The new server, so actually I said initially what we were doing was 210 times 210 comparisons. That's actually blown up a little bit because we got some more data since that initial result, and it's another Hamby set. Essentially what we're working with now is more like 200,000 cross comparisons, and we can compute all 200,000 cross comparisons in about 30 minutes on this server. So if we got a new bullet, compared to all the other bullets, it would be a fraction of that, and it would be very quick. So it's improved. Another question?
With the original experiment, the match probability seems much more conservative than the resulting spec and sensitivity indicate which were perfect scores.
Can you maybe repeat it? Go back.
With the original experiment, the match probability seems much more conservative than the resulting spec and sensitivity indicate, which were perfect scores.
So the we definitely don't have a perfect. Do you have a comment?
Between matches between lands and matches between bullets.
Good point. I get it now. So the original experiment was all doing bullet to bullet matching procedures, and we did it on the land to land level. I didn't put this in the slides because I didn't have time for this, but we actually did generalize our algorithms to do bullet to bullet matches, and we were able to perfectly distinguish all bullets with no errors. So a specificity and sensitivity of 100%. Using full bullets, depending on your assumption. So that's the difference. We're making more errors than the original study because we're doing it land to land versus bullet to bullet, but with bullet to bullet, we can also achieve those results. Good question. Question here, yep.
How you determine what features you use? Were they similar to like the features that were used earlier when like the signatures were obtained like manually?
Yeah, so it was sort of a little bit of an ad hoc process. So we knew CSAFE was a common one that's been used, and it's in the literature quite a bit. We knew CMS was a common one, so we kind of started with that, and then we started thinking like, what are some other features that could actually distinguish between the profiles? And I think the ones that had not been used quite as much were things like the actual vertical difference between the two signatures. So we wanted to include that. And then we also wanted to see whether there's actually importance to the consecutive portion of the matches versus just how many matches you have. And so it was a bit of an ad hoc process of thinking of what features could be important, trying them, and then looking at the importance and optimizing it from there. That's a good question.
Do you take any measures to guard against the
Any
possibility?
others?
Hello?
Do you hear me?
Okay, thank you.
Question. Yep. Go ahead, whoever had a question.
I don't care.
You had a question?
Yes.
Oh, do you hear me now?
Yes.
Do you take any measures against the possibility that there could be multiple areas of local stability in the CCF as you travel down the axis of the bullet?
The question is, do you take any
Measures to test for that, or to, what do you do if that happens? Because it could.
Do you take any
This isn't working very well.
As we search across the bullet, is that to find where to extract?
Did I get your question correct, sir?
I'm not sure, because it break up a bit for us too.
Okay, go ahead and repeat your question, sir.
Traveling down the axis of the bullet.
Go ahead.
Traveling down the axis of the bullet,
Traveling down the axis
there's a
of the bullet.
possibility that you could encounter local stability in the CCF, but if you go on further, there could be additional spots where it would be stable. What do you do about that?
Hold on 1 second, sir.
Okay.
All right, sir, go ahead. Right, sir, go ahead. Repeat the question.
We're going to try to type in the question since we're having trouble with the audio.
All right, the question reads, possibility of multiple areas of local stability in the CCF.
Across the different parts of the bullet. That's absolutely true. So what we're doing is we're essentially taking the very first on a search from the base of the bullet and using that. We are starting to explore either using other locations where we extract the signature higher up on the bullet if it's stable and if it has the striations, or doing a mean profile. So sort of rather than just using one single fixed axis, computing kind of an average across all of that region where there might be striation markings. That involves a little bit more because of the axis of the striations is not perfectly vertical. So we sort of need to adjust for the tilt of the land before we can do that, which is part of why we stayed just with extracting a single profile. But it's something that's continuing to be explored.
Final question. The main utility for the CMS is the empirical determination of the agreement seen in known non-matches, and where the examiner must be careful in declaring a match in minimum agreement. That is a way to warn the examiner to not make a match in these instances where the agreement is due to coincidental agreement between two tool-marked sources.
Yeah, so I hope I didn't give the impression that like I think CMS is useless. I think the basically the idea in my mind is that the CMS makes a lot of sense as a criteria to be used when you're manually examining the surfaces of the bullet, because we can't mentally look at the striation markings and compute a CCF. We can't compute most of the features we did, but once we do have it pared down to data, we can go a little bit beyond CMS and have some more features as well. But I definitely agree it's useful for the forensic examiner as a sort of a benchmark. Yep, another question?
How are you aligning the scans and protecting against possible bias?
So we're aligning the signatures by using the CCF. So essentially finding the location at which the correlation is highest between the two signatures when we're shifting one of the signatures across the other. We're not actually doing any alignment of the scans themselves because we extract the profiles individually from each scan before we do the alignment step.
You describe the process for extracting initial situation or striation profile and how you find good location by using a CCF greater than 0.9 between consecutive slices. But how do you determine the orientation of the extracted slice?
Great question. We actually, that's kind of a issue that goes along with the tilt, because we actually don't take into account the orientation. So we extract the slice across that particular coordinate value through the whole profile. So if there is a tilt in the actual striations, we're not accounting for that. It ends up not mattering too much for us because if I go back to one of these surfaces, if we extract along one of these coordinates and we're off by a little bit, we're actually doing the same for the other bullets and extract. And so the tilt is the same in this case for all the different bullet lands that are part of this data set. But definitely we should probably be horizontally adjusting this, or the initial scan should have been horizontally adjusted prior to that step.
If you extract at the wrong angle, it will manifest as dilation or shrinkage of the profile.
Yes, I agree with that. Yeah, so essentially if we're extracting at an angle that's not perfectly horizontal to or perpendicular to the striations, it would manifest like that. So I think it's definitely potential that we could improve the algorithm if we did that rotation before we did the extraction step. Okay, thank you again. Yep.